Hello, I am Krish Modi and I will go over the part 1 of the Lab 7. The implementation uses a two-layer multi-layer perceptron built entirely in NumPy. The architecture consists of an input layer, a hidden layer with ReLU activation, and an output layer. For regression tasks, we use raw outputs, while classification tasks, we use softmax activation. We implemented two loss function, mean squared error for regression and cross entropy for classification. The network is trained using stochastic gradient descent with many batches. All weights are initialized using key initialization, which is specifically designed for ReLU networks. This implementation demonstrates the fundamental building blocks of neural networks without relying on high-level frameworks. The MLP2 class encapsulates all neural network operations. The forward method performs matrix multiplication and applies activation to generate predictions. The backward method implements backpropagation, computing gradients using the chain rule from calculus. The step method updates all parameters using these gradients and the learning rate. Our training infrastructure includes a batch iterator that shuffles data each epoch and a training loop that tracks loss over time. We also implemented numerical stability measures such as subtracting the maximum value before computing softmax to prevent overflow and adding a small epsilon to logarithms to avoid undefined values. The code is modular and supports both regression and classification with a simple mode parameter. Our analysis script provides automated evaluation and visualization for all three experiments. Each analysis function loads data, trains a model, and generates comprehensive visualizations that you'll see in next slides. For regression, we plot training loss, function approximation, residuals, and prediction scatter plots. For classification tasks, we visualize training data, decision boundaries, and test results with correct and incorrect prediction marked. The script is designed to be run independently and generates publication quality plots that help us understand model performance and behavior. All plots are saved automatically for inclusion in reports and presentations like these. We design the analysis with separation of concerns in mind. The MLP implementation is completely independent and can be imported and used in different contexts. The analysis script focuses solely on evaluation and visualization. This modularity makes the code maintainable and testable. We measure comprehensive metrics, including training convergence through loss curve, quality of function fitting using residuals, and classification performance through decision boundaries and accuracy metrics. All experiments use fixed random seeds for reproducibility, meaning anyone can run our code and get identical results. The automated pipeline ensures consistency across all three experiments, making comparisons meaningful and fair. Our first experiment tests the network's ability to approximate a piecewise linear function with added noise. We used a simple architecture with 32 hidden units. The network was trained for 500 epochs with a learning rate of 0.01. Looking at the results, the training loss plot on the top left shows rapid initial decrease, then stabilization around epoch 150 at an MSE of 0.0018. The function approximation plot demonstrates excellent agreement between predicted and true values. The blue dashed line closely follows the red solid line. The residuals plot shows random scatter around zero with no symmetric bias, indicating proper model fitting. The predicted versus true scatter plot closely follows the perfect prediction line, confirming accurate learning. The MSE of 0.0018 means predictions are typically within plus or minus 0.042 units of the true value, which is excellent given the noise in the training data. The second experiment tests nonlinear classification on a concentric rings dataset, which is not linearly separable. We increase the hidden layer to 64 units to compute the radial decision boundary. The training loss decreased steadily from 0.75 to 0.375 over 200 epochs. The training data plot shows clear separation between red inner ring and blue outer ring points. The decision boundary visualization is particularly interesting. The contour plot shows smooth circular regions correctly separating the two classes. The network successfully learned the radial pattern using only rectangular operations and ReLU activations. Our test accuracy of 95% indicates excellent generalization with minimal overfitting. Despite the training accuracy being 97.34, most misclassification occur at the boundary region between rings where noise creates ambiguity. This demonstrates the network's ability to learn complex nonlinear decision boundaries. Our final experiment demonstrates multi-class classification on three Gaussian clusters. The network architecture is similar to binary classification, but with three output units. Training loss decreased smoothly from 0.78 to 0.16, indicating stable optimization. The training data visualization shows three well-separated clusters in red, blue, and green. The decision region plots is crucial here. It clearly shows three distinct colored regions corresponding to each class. Notice how the boundaries between regions are smooth and properly positioned between cluster centers. Interestingly, our test accuracy of 97.78 actually exceeded training accuracy of 94.31, which indicates the model generalization well without overfitting. Only 4 out of 180 test samples were misclassified, primarily in overlapping regions between clusters. This experiment validates that a simple two-layer network can effectively handle multi-class problems with proper softmax activation and cross-entropy loss. To summarize part 1, we successfully implemented a two-layer multi-layer perceptron from scratch using only NumPy. The implementation handles both regression and classification tasks through a unified framework. Our experimental results validate the correctness of the implementation. The regression task achieved on MSC of 0.0018, binary classification reached 95% accuracy, and classification achieved 97.78% test accuracy. Key insights from this work include ReLU activation is essential for learning nonlinear patterns. Proper weight initialization using the key method is crucial for training stability. Mini batch SGD provides a good balance between computational efficiency and gradient accuracy, and a simple two-layer network is sufficient for these synthetic tasks. The hands-on implementation provides deep understanding of neural network fundamentals that are abstracted away in modern deep learning framework. Understanding these building blocks is essential before moving to more complex architecture like CNNs and transforms, as my two teammates will explain in part 2 and 3. Thank you.
Hi, here let's walk through comparing the same image classification task which are done in two ways. A small CNN on CPU with NumPy and the same task on GPU with PyTorch. The point is to see what changes in speed and accuracy when we switch to GPU. So the plan is simple. We implement a small CNN on CPU, then rebuild the workflow in PyTorch on GPU and compare the results end to end. The same dataset, same goal, just different tooling and hardware. We used 25,000 images of cats and dogs, 20K to train, 5K to test, and all RGB 64 cross 64. The GPU side, I ran PyTorch plus CUDA on two Tesla T4s batch size of 128 4 workers using data parallel. So data loading step alone dropped from 147 seconds to roughly 0.3 seconds, and that's 492 times faster just from efficient loaders. This slide shows the CPU baseline. Think of it as minimal CNN trained the straightforward way. Useful as a reference point but limited in throughput. So notice this lower iteration speed. We'll use this to benchmark the GPU later. So here's the PyTorch version. The data pipeline has image folder plus data loader with 64 cross 64 transforms. The model is a small CatDog CNN with 3 convolutional blocks and batch norm, then fully connected layers. The device setup is like moving the model's tensors to CUDA. And the optimizer, which is a Atom with a standard learning rate. The big win is that all of this runs efficiently in batches on the GPU. So this page is a quick hardware reminder. So we are leveraging two T4 GPUs with CUDA. The takeaway is that even modest data center GPUs can massively accelerate this workload without changing the task itself. This is the confusion matrix of CPU. Before we jump into final metrics, so this is it, and you can see more mistakes, especially misclassifications, that we'll cut down once we move to GPU model. So keep this visual in mind as context for the accuracy jump that you'll see next. Here are the headline metrics. So the accuracy jumps from 55% to 80%. The training time drops from 5,499 seconds to 213 seconds. That's 25 times faster. The inference time goes from 147 seconds to 9.36 seconds. That's 15x faster. And the data loading goes from 147 seconds to 0.3 seconds. That's about 492x faster. Next, we'll move to code explanation.
Hey everybody, I'm Aditya and I'm here to walk you through the explanation of the part 2 and part 3 of Lab 7. Essentially, in part 2, we implemented a CNN entirely from scratch using NumPy without relying on any deep learning libraries. It aims to provide a fundamental understanding of how convolutional operations, pooling, activation, and backpropagations are executed at the array manipulation level. So the first step was data loading and pre-processing. The dataset is first loaded and normalized so that the pixel values range between 0 and 1. Each image is reshaped into fixed input dimension suitable for convolutional operation, right? And the labels are created based on the image title name. Usually in this case we are dealing with a binary classification. So if it is a cat image, it would be 0. Else for a dog image, it would be 1. So the purpose of this was to normalize inputs for stable training and prepare data tensors manually using tensors manually, since NumPy lacks a data loader abstraction. Then we split the dataset into 80-20 halves, where 20% would be set aside for testing purpose and 80% of the dataset would be kept for training the model. Then we implemented the architecture, the network CNN architecture. We defined convolutional layers, activation functions, and max pooling layers. in the architecture. Uh, so the convolution layer 1 applies a small set of filters to extract local spatial patterns like edges and corners. The ReLU activation function was used to introduce non-linearity to capture non-linear patterns within the images. Pooling layer reduces the spatial dimensions while retaining important features, and the flattening step converts 3D output into 1D vector for dense layers. The purpose was to simulate how a real CNNs extract hierarchical features implemented via raw NumPy operations like now an np dot dot, np dot sum, and np dot max. This is the forward propagation function. This section defines how the input passes through the CNN. Each convolution and pooling layer performs explicit array manipulation. The convolution uh, the convolution loops over the spatial locations, computing weighted sums between filters and local image regions. ReLU sets all negative activations to 0, and pooling the max pooling here downsamples the feature maps. Finally, the fully connected layer combines the extracted features to output class probabilities. The purpose of this section was to calculate the predicted output for each input sample using matrix operations built from scratch. In this, we initialized yeah, essential parameters utilized for the training. For example, the convolutional filter, the weight matrix for the fully connected layer, and the bias matrix for the fully connected layer. The learning rate was 0.001, and number of epochs the training ran for was 10. This is where we were starting our clock to keep a track of how much time will it take to train the whole data set. And this is essentially the training loop of uh, of the whole data set, and we are traversing through the whole training data, and this is the forward propagation for a particular image, and then we calculate the loss function, a loss using MSE loss. Here the loss function which was utilized was mean square error uh, loss, which is defined up here, and and once the loss is calculated, this loss is appended into the total loss for the particular epoch, and then this from this section onwards we back propagate using the using while calculating the derivatives with respect to weights and biases, and then we then update the weight matrix and the bias matrix using the formula. And then the whole purpose was to execute a full training cycle of a CNN purely with NumPy logic, giving insight into computational cost and memory requirements. Then we saved the model weights into a NumPy file. And this section deals with the evaluation, where after training, the model's performance is tested on a separate test set, which was kept 20% of the data set. The predicted outputs are compared against the ground truth labels to compute accuracy. The purpose of this section was to verify the correctness of the manually implemented CNN and assess its ability to generalize. And these were the different metrics which were calculated: the true positive, true negative, false positive, and false negative, which were essential components for the confusion matrix in a binary uh, class classification. And these were the comprehensive print statements that were used, and the different model performance metrics like the test accuracy, precision, recall, and F1 score. And this was the dataset statistics where we reported the total number of images processed, the training sets size, the test set size, image resolution, and the flattened feature size. And once all the evaluation was done, we saved it into a NumPy array and called it evaluation underscore results.npz. And this was the code for the graph to plot the MAC plot across across 10 epochs, and the code for plotting the confusion matrix using the TP, the true positive, true negative, false positive, false negative values. And this was the combined plot for both loss function and the confusion matrix. So moving on to the part 3, which was PyTorch CNN with GPU acceleration. So the first part, you can see that these are the essential imports that were required for the Python script. And then we begin by importing essential PyTorch modules like Torch, Torch.nn, Torch.optimizer, and Torch Vision. The next set of lines check the availability of CUDA, whether CUDA was available within our machine, and how many CUDA cores were available for training. Then we moved on to the custom dataset creation for faster loading. The data is loaded using a PyTorch data loader, which automatically manages batching, shuffling, and prefetching. The Torch Vision.transforms module handles normalization and tensor conversions, simplifying pre-processing compared to the manual NumPy approach. And this was a custom data loader which was used using the dataset torch imported from torch.utils.data. This helped us to create a custom data set from our data directory. This was the transformation functions which helped us to resize each image as 64 cross 64 and normalize them based on these mean and standard deviation values. These were the transformations which were given to the tester dataset. So firstly, we loaded the whole dataset using the custom dataset loader, which is defined up above here. And then we split the dataset into 80-20%. After the manual split, we created a separate dataset with different transforms, and we applied those transforms, the train transform and test transforms. Then for data loading, we used a 128 batch size and 4 workers for parallel data loading to keep the GPU engaged during the training process and maximize the GPU utilization. This was the data loader for the training data set. This the shuffle equals to true indicates that during every epoch, the data set is shuffled again. The batch size was 128. The number of workers were 4. Pin memory true indicates that it has faster data transfer to GPU, reducing the idle time for a GPU. The similar configurations were created for the test data set loader. Once the data loaders were created, we defined the CNN network. The CNN network is defined by subclassing nn.module with standard layers such as nn.conv2d for convolutional filtering, nn.relu for nonlinear activation using ReLU function, the nn.maxpool2d for downsampling, and nn.linear for fully connected layer. Each layer is registered automatically within the model, enabling PyTorch to manage gradients and updates internally. Then the def.forward function defines the forward propagation for a particular image. The forward function defines the data flow through the network. The PyTorch automatically constructs a dynamic computational graph, recording operations for automatic gradient computation during backpropagation. The purpose of this is to define mathematical pipeline of the CNN while allowing flexible experimentation with the architecture. Then we initialize the model and we use the data parallel, which is part of the torch.nn.parallel module, which essentially puts two copies of the model on the number of available GPUs present on the particular device. And then we move the model to the device, one which is a GPU in this case. The data parallel enables multi-GPU training with coordinated weights and bias sharing. And then here we printed out the model architecture and calculated the number of trainable parameters that were used for training the model. In the loss function, we incorporated a binary cross entropy for binary classification, an Adam optimizer with a learning rate of 0.001, and a learning rate scheduler, which is a reduce LR on plateau. Uh, Now moving forward towards the training loop. Uh, the training loop was it ran through 10 epochs. The first initially it transferred data and labels to the GPU memory. We performed the forward pass and calculated the loss. Then we computed the gradients using loss.backward and optimizer.step. And after computing the loss, we added the particular loss to a epoch loss, and we we then updated the weights using optimizer.step. Then resetting the accumulated gradients via optimizer.zero_grad. The purpose was to execute efficient and parallelized training cycles leveraging GPU acceleration and autograd. This is the particular epoch loss and epoch accuracy and the time taken for the particular epoch to run. This after After training the model, we saved the model in a .pth file and evaluated the model on the 20% dataset which was uh, kept aside earlier. With the torch.nograd, which indicates that no gradients would be computed during the forward after the forward pass, we first then utilized uh, the we first then moved the images and labels to the GPU, calculated the forward pass to compute the loss, and added the total and the accuracy. And these variables were used for the confusion matrix. The inference time was the time it required to compute the whole inference pipeline on the 20% data set kept aside. Then we had accuracy and different metrics being calculated using true positive, true negative, false positive, and false negative, precision, recall, and F1 score. These are the different print statements for creating a comprehensive report. And the timing analysis, which we use to calculate the load time, the training time, time per epoch, etc., etc. This was the part where we indicated the hardware utilization of the device, the number of GPUs, and batch size and number of workers that were utilized. So these were the different metrics that were calculated. And then we compared it with the NumPy version. We first loaded the NumPy results, and then we extracted the training time, the inference time, and the accuracy. Then we compared how much was the NumPy version and the PyTorch GPU version, and benchmarked the speed up that was required in that took place from navigating from NumPy to PyTorch. Then this was the plot of the training loss, and this was the plot for the training accuracy. And this is the plot for the confusion matrix, plotting the true positive, true negative, false positive, and false negative values. And this plot compared the performance between the NumPy CPU implementation and PyTorch GPU implementation. Then we saved the results into an NPZ file and kept MPC file, which is PyTorch underscore results.mpc. Thank you.